subgroup of G if H itself forms a group under the same binary operation. The same definition is for the subspace also. A non-empty subset W of a vector space V over a field F is said to be a subspace of V if W itself forms a vector space over F with respect to the same operation of addition and scalar multiplication defined in V.
Sir, excuse me.
Yes.
Sir, some students are waiting.
I have already invited everyone.
सर उनके पास मेल नहीं आया था.
तो हम क्या करें बताओ?
सर वो वेट कर रहे हैं, मैसेज कर रहे थे ग्रुप में.
देख लेता हूँ उन्हें आईडी बता दिया तुम लोगों ने. कहाँ पर field F is a subspace if W itself forms a vector space under the same operation. Whatever is the operation for V, the same operation should be for W, then it will be a subspace. For any vector space V over a field F, 0 and V are always subspaces of V called trivial and improper subspaces of V. All subspaces of V other than these two are called proper subspaces, just like the definition of trivial subgroup or trivial subring. For any vector space, these two are always subspaces, and there may be subspaces other than these two, they are called proper subspaces. The necessary and sufficient condition for a non-empty subset W of a vector space V over a field F is said to be subspace of V. And now, so far by the definition, any non-empty subset is a subspace if W is a vector space. It means that we have to show that W plus is an abelian group. Then W is closed under scalar multiplication and last four conditions are satisfied. Therefore, there are 5 conditions here. There is 1 condition here and there are 4 conditions here. So total there are 10 conditions. But if we know this result, that is remark 2, then by using just 2 conditions, we can say that any subset is a subspace or not. So the necessary and sufficient condition for a non-empty subset W of a vector space V over a field F is a subspace of V. If W is closed under vector addition, it means that X plus Y belongs to W for any XY belongs to W. W is closed under vector addition and scalar multiplication. It means that alpha X belongs to W for any alpha belonging to F, X belonging to W. If these 2 conditions are satisfied, then any non-empty subset becomes a subspace. These 2 conditions are now reduced to a single condition by this result. This is a theorem which we have proved in graduation. Any non-empty subset W of a vector space V over a field F is a subspace of V if and only if alpha X plus beta Y belongs to W. Instead of we say that it is closed under addition and scalar multiplication, we say that alpha X plus beta Y belongs to W. Then these 2 conditions will be satisfied. Alpha X plus beta Y belongs to W. If you put alpha is equal to if you put alpha is equal to beta is equal to 1, alpha X plus beta Y belongs to W. If you put alpha is equal to beta is equal to 1, then this implies X plus Y belongs to W. And if you put alpha is equal to alpha, beta is equal to 0, then this becomes alpha X belongs to W. So this is the first condition, this is the second condition that is here. Therefore, by using just 1 condition, we can check that whether any non-empty subset is a subspace or not. Alpha X plus beta Y belongs to W for any XY belongs to W and alpha beta belongs to F, then it is said to be a subspace. For example, if you consider this one, W1 is equal to 0, 0, Z such that Z belongs to R. You consider two elements, XY belongs to W1 such that X is equal to 0, 0, Z1, Y is equal to 0, 0, Z2, alpha, beta belonging to R, alpha X plus beta Y is equal to alpha 0, 0, Z1 plus beta 0, 0, Z2 is equal to 0, 0, alpha Z1 plus 0, 0, beta Z2. That is equal to 0, comma 0, alpha Z1 plus beta Z2. This is also the element of R. Therefore, this is the element of W1. Alpha X plus beta Y belongs to W1. It means that W1 is a subspace.
Yes, sir.
Yes, sir.
Okay. Do you see that? Secondly, if we have W2 is like this, on the similar lines, we can show that this is a subspace. So these two are subspaces because we have checked this condition. Alpha X plus beta Y belongs to W. Now, just like the properties of subgroup and subring, the intersection of any two subspaces of a vector space is also a subspace. But the union of any two subspaces is subspace. For example, here you see that W1 and W2 are subspaces. If we take the union of these two, then it is not a subspace. Why? Because if we pick one element here, this is the element of W1, this is the element of W2. Now W1 is contained in W1 union W2. W2 is also contained in W1 union W2. Therefore, this is the element of W1 union W2. This is the element of W1 union W2. So these two are the elements of W1 union W2. Now to show that W1 union W2 is a subspace, if we have to show this, then we have to show that it is closed under addition and scalar multiplication. So now these two are the elements 0, 0, 3, 0, 5, 0. These are the two elements of W1 union W2. Now if we take the sum of this, because to check the closure property under addition, this is equal to 0, 5, 3. Now this is not the element of W1 union W2 because you know that if there is any element which is the element of A union B, then we must have X belongs to A or X belongs to B. If there is any element in the union, then either it is the element of A or it is the element of B. But this element, this is neither the element of W1 nor the element of W2. So that's why this element is not the element of the union because neither it is the element of W1 nor it is the element of W2. So therefore, it is not closed under addition. So this is the sufficient condition. It means that this is not a subspace. The union of any two subspaces need not be a subspace, and the example is here. The union of these two is not a subspace, but the intersection of any number of subspace is always a subspace. Just like the properties in subring ideal, the union is a subspace if and only if one is contained in the other. The union of any two subspaces of vector space may be a subspace provided that one is contained in the other. Now we shall check some examples here. Let V be the real vector space of all functions f from R to R. So V is equal to f such that f from R to R. Which of the following sets of functions are subspaces of V? The first one is W. W contains those elements of V such that f of x square is equal to f of x whole square. If W is a collection of elements of those elements of V which satisfies this condition, then we have to check that whether it is a subspace or not. Similarly, W is the collection of all elements of V which satisfies this condition. W is the collection of all elements of V which satisfies this condition. W is the element of those elements of V which satisfies this condition. So therefore, we have to check in these cases one by one whether it is a subspace or not. So first of all, we consider the first case. W is equal to F such that F belongs to V and Fx square is equal to F of X whole square. So clearly, W is a non-empty subset of V. You see that this contains the elements of V, therefore it is a subset of V. And of course, this F can be replaced by zero function, is 0 from R to R, which maps every element to 0. This is 0 belongs to V such that 0x square is equal to 0 and 0 of x whole square is also 0. Therefore, this condition is satisfied. It means that this 0 is the element of W. Now, to show that it is a subspace, we shall prove that alpha F plus beta G belongs to W for any Fg belonging to W and alpha beta belonging to R. We have to show this condition if it is a subspace. Otherwise, if it is satisfies this condition, then it is not a subspace. So we consider two elements here. First element is F. It means that this condition is satisfied. Second element is G. In place of F, this is G here, this is G here, this is G here, and this is G here. So these two are the elements. Now we have to show F and G belongs to W. We have to show alpha F plus beta G belongs to W. W is collection of those elements of V such that F of X square is equal to F of X whole square. In place of F, if we write this here, and if it is same as if we put the value of F in the right side. So first of all, we check the value of putting alpha F plus beta G in place of F in the left side. This is left hand side and this is the right hand side. So we check these two values one by one. So first of all, the left hand side, this is left hand side, alpha F plus in place of F, this is alpha F plus beta G of X square. You see that, remember that this alpha and beta are real numbers. F and G are functions from R to R. So therefore, just by using the properties of functions, it can be written as alpha F of X square plus beta G of X square. So alpha F of X square plus beta G of X square. Again, you know that constant time F of X, that is equal to C of Fx. This is the general formula for any function. So therefore, this is equal to alpha of Fx square plus beta of Gx square. Now F belongs to W, therefore Fx square is equal to F of X whole square. Therefore, this is F of X whole square. Similarly, G belongs to W and therefore G of X square is equal to Gx of whole square. Therefore, G of X square is equal to Gx of whole square. So this means that alpha F, this is the left hand side. Replacing F by alpha F plus beta G. Therefore, we get this value as the value of this. Now we find the right hand side. We replace F by alpha F plus beta G. This is the right hand side. Alpha F plus beta G of X whole square. Again, by using the properties of functions, this is equal to alpha F of X plus beta G of X whole square. Now, you see that F and G are functions from R to R. x is the element of R. Therefore, fx is the element of R. It is a real number. So therefore, now alpha fx, alpha is a real number, fx is a real number, this beta is a real number, gx is a real number. So therefore, the product of two real numbers is a real number. So this is a real number, this is a real number. So this is just like a plus b whole square. So we put the value of a plus b whole square. A square means alpha square f of x whole square plus beta square g of x whole square plus the product of these two, 2 times alpha beta fx into gx. So now you see that the left hand side, this is left hand side, this is equal to this is the right hand side, this is equal to this. So you see that clearly these two values are, they may be equal for some particular values of alpha beta, but for a subspace it should be true for all xy belongs to w, for all alpha beta belongs to R. If alpha x plus beta y belongs to w, then it is a subspace. Otherwise, if there exists a pair of elements of w or a pair of elements of R where this is not the element of w, then it is not a subspace. So you see that one side its value is equal to this, on the other hand its value is equal to this. So this is the left hand side and right hand side, and these two values are not equal for every alpha beta. So therefore, these two values are also not equal. This is not equal to this. And if it is not equal to this, it means that we cannot put alpha f plus beta g in place of f here. This means that alpha f plus beta g doesn't belongs to w. Therefore, w is not a subspace. So we have seen that in the first case, if this condition is satisfied, then it is not a subspace. किसी को कोई confusion तो नहीं?
No, sir.
Okay. Now in the second case, f0 is equal to f1. So w is equal to f such that f belongs to v and f0 is equal to f1. We have to check that whether it is a subspace or not. So first of all, we consider two elements here. The first element is f. If we consider g here, so in place of f, this will be g here throughout. G of 0 is equal to g of 1. It means that we have two relations, f0 is equal to f1, g0 is equal to g1. Now we shall use this one to show that alpha f plus beta g, it is the element of w or not, or this is not the element. So now to show that alpha f plus beta g is here or not, so we write in the left hand side. This is the left hand side. We find the value of left hand side. Alpha f plus beta g of 0. That is equal to alpha f of 0 plus beta g of 0. Alpha of f0 plus beta of g0. And f0 is equal to f1. Similarly, g0 is equal to g1. Alpha of f1 plus beta of g1. Alpha f of 1 plus beta g of 1, just by using the properties of functions. This is equal to alpha f plus beta g of 1. So you see that the left hand side is equal to right hand side. So this condition is satisfied for alpha f plus beta g also. This means that this is the element of w, and therefore w is a subspace of V. In the third one, all f such that f of 3 is equal to 1 plus f of minus 5. You see that whenever we say that w is a subspace, it means that w plus is an abelian group. And therefore it must have identity element. And you know that whenever we have a functions from collection of V is a f such that f from R to R, collection of all functions, it is a vector space. Therefore its additive identity is a mapping 0 from R to R such that 0 of x is equal to 0. This is the additive identity of V. that must be the additive identity of W also, because in a group, the identity of a group is same as the identity of its all subgroups. So this 0 must be the 0 of this. But if you put here, you see that in the third case, if you replace f by 0, then 0 of 3 is equal to 0. This is 0 mapping. And if you put 0 here, then 1 plus 0 of minus 5 is equal to 1 plus 0, that is equal to 1. So left hand side is 0, right hand side is 1. It means that 0 is not the element of this W. So either you mention that since W, which is the collection of all F, such that F belongs to V and F of 3 is equal to 1 plus F of minus 5, you see that 0 is identity of V, but 0 is not identity of W, since 0 of 3 is equal to 0 and 1 plus 0 of minus 5 is equal to 1. Therefore 0 is not equal to 1. So that's why identity is not there. So for a subspace, identity must be there. So this is one of the reasons that it is not a subspace. Otherwise we check the condition like this. So we have checked the condition here. Otherwise you mentioned that 0 is not the element of W. So for checking the condition, we consider two elements of W, two elements of R, alpha F. Now we find the left hand side. Alpha F plus, you replace F by alpha F plus beta G. Alpha F plus beta G of 3, alpha F3 plus beta G3, alpha F3 plus beta of G3. And now you put the value of F3. F3 is equal to 1 plus F of minus 5. You put this value here. Similarly, G3 is equal to 1 plus G of minus 5. You put this value here. Therefore, simplifying it, this is alpha into 1 alpha, beta into 1 beta, alpha plus beta. Plus combining this into this into this is alpha F plus beta G of minus 5. Now it should be equal to alpha, in place of F, alpha F plus beta G, in place of F, alpha F plus beta G. It means that in the first term it should be 1. But here we obtained that this is alpha plus beta. So there are many alpha betas. This is the element of R. There are many alpha betas where the sum of alpha plus beta is 1. Like 1 upon 3 plus 2 upon 3 is 1. But there are also many alpha betas where this is not equal to 1. 2 plus 5 is not equal to 1. So there are many alpha beta belonging to R where the sum is not equal to 1. So it is not always equal to 1. This value is not always equal to 1. That's why this condition fails here. Therefore, this is not a subspace. Finally, in the fourth one, f of minus 1 is equal to 0, all f. We check this one. F such that f belongs to V and f of minus 1 is 0. Now we consider two elements here. G belonging to W and alpha beta belongs to R. Alpha f plus beta G of minus 1. Alpha f of minus 1 plus beta G of minus 1. Alpha of f of minus 1 plus beta of G of minus 1. F of minus 1 is 0, G of minus 1 is 0 similarly. It means that alpha into 0 plus beta into 0. So whatever is the value of alpha and beta, alpha into 0 is always 0. Similarly, beta into 0 is always 0. This means that this value is always 0. And therefore, this is the element of W. And therefore, W is a subspace of V. So in these four examples, किसी को कोई ऐसा है जिसको कुछ दिक्कत हो कहीं पे?
No, sir.
Okay. So now you see that R3, we have discussed yesterday that Rn R is a vector space. For every value of n, it is a vector space. Now R3R and R2R are vector spaces. Now, if we ask whether R2 is a subspace of R3 or not, this is a vector space. This is a vector space. But R2 is not a subspace of R3 because you see that R2 for a subspace, W is a subspace of V if W is non-empty, W is subset of V, W is a vector space under the same condition. So this condition is not satisfied here. For a subspace, it should be a subset, but you cannot say that R2 is a subset of R3. Because for a subset, A is a subset of B, every element of A is the element of B, A belongs to B, then we say that A is subset of B. But R2 is not a subset of R3 because AB belongs to R2, but AB doesn't belongs to R3. So R2 is not a subset of R3. But for a subspace, it must be a subset and then satisfying the conditions for vector space, it will be a subspace. So R2 is not even a subset of R3, as vectors in R3 have all the three entries, whereas vectors in R2 have only two. So you see that R2 means if you have a plane X and Y, suppose that you measure two distance here, 2 and 1 here, then this is 2, 1. This is the element of R2. 2, 1 is the element of R2. But whenever you consider the R3, this is the case of R2, and when we consider R3, then there are three axis here, x-axis, y-axis and z-axis. If we have to find 1, 2, 3, then on x-axis we have to measure one distance, on y-axis we have to measure two distance, on z-axis we have to measure three distance. Now if we draw perpendicular by 3 and their intersection will give you the point 1, 2, 3. You have to measure one distance on x-axis, 2 unit distance on y-axis, 3 unit distance on z-axis. You draw perpendicular from there, and the point of intersection will be the point given by 1, 2, 3. So R2 and R3 have different sets. You see that there are every element is in ordered pair. Here every element is ordered triad. So that's why R2 is not even a subset of R3. So that's why it cannot be a subspace. But if we consider a similar type of set like XY0, so when we say XY0, then every point here is here. Only this axis is in our mind. There is no role of this axis, but for example, if you consider 2, 1, 0, then you have to measure two distance here, one distance here, and 0 distance here. So therefore, the point of this intersection is equal to 2, 1, 0. So it acts and looks like R2, but it is logically distinct from R2. So this is looks like R2, but it is logically distinct from R2. So that's why this is not equal to R2. This is a subset of R3, which also form a subspace. That's why it is a subspace. So this is a subset as well as subspace of R3. A plane in R3 not through the origin, like 1xy. It means that if we take this distance 1 unit, we fix it, and all other points here means this is fixed. It means that this is a plane passing through 1. This is not a subspace of R3 because we have mentioned here that for a subspace it should be containing the 0 vector also. A subspace is also a subgroup, so it should contain 0 vector also, but it cannot contain 0. 0, 0, 0 is not the element of W. This W, because first slot is fixed here, that is 1. So it cannot contain this vector, which is the additive identity of R3. So therefore, this doesn't contain the additive identity. That's why it cannot be a subgroup under addition, and that's why it cannot be a subspace. So a plane passing through one. This is a plane. This is also a plane, xy plane. And here, this is a plane which passes through one. So this is not a subspace of R3 because W is not containing the zero vector of R3. Similarly, a line in R2 not through the origin is not a subspace. If we consider R2, any line through the origin is a subspace. This is a subspace. But this is not a subspace because this doesn't contain 0, 0. 0, 0 is not the element of this line. It is the element of this line. So any line through the origin in R2 is a subspace, but any line not through the origin is not a subspace. Like if you consider a line like 1x such that x belongs to R. This is a line, but it is not passes through 0, 0. So that's why this is not a subspace of R2. Next definition is the definition of linear combination. As we have discussed that any vector space is closed under addition and scalar multiplication. Whenever we say that V is a vector space, then there are two binary operations, internal and external. So any vector space is closed under addition and scalar multiplication. So therefore, if V1, V2 up to Vn, यहाँ पर देखो ये गलती है थोड़ा सा, यहाँ पर V कर लेना. V1, V2 up to Vn are any elements of V, then alpha 1 V1, this is the element of V. By V is closed under scalar multiplication. This is the element of V because V is closed under scalar multiplication. This is the element of V because it is closed under scalar multiplication. And the sum of all these is also the element of V because it is closed under vector addition. Therefore, the sum of all these, alpha 1 V1 plus alpha 2 V2 plus alpha n Vn, this is also the element of V, and it is called linear combination of vectors V1, V2 up to Vn. So when we say that linear combination of V1 and V2, it means that alpha 1 V1 plus alpha 2 V2 or alpha 1 V1 plus beta 1 V1 V2. So I stop here. जिन लोगों को भी इनविटेशन मेरा नहीं पहुंचा है मेल से, वो अपना मेल आईडी मुझे कर देंगे, मैं जिस टाइम भी फुर्सत मिलेगी अवॉइड कर देंगे, ठीक है. और अगर किसी को नहीं पहुंचा हो तो क्लास पे आया करो. ग्रुप में इधर उधर मैं मोबाइल देखता नहीं हूँ. मोबाइल 24 घंटे में एक आधी बार देखता हूँ. अटेंडेंस तो मिला है नहीं तुम लोग की, इसलिए आज अटेंडेंस नहीं होगी, ठीक है ना. तो दैट्स ऑल फॉर टुडे. थैंक यू.
Thank you, sir.
वेलकम.